Alternating current fundamentals. Number 1. Magnetism and electromagnetism.
Electricity is used to meet the world's constant demand for energy. Whenever you flip on a light switch, prepare a meal, or simply relax in front of the television, you depend upon this vital source of energy.
Much of the electrical power used in the world today, up to 90%, is alternating current, or AC. The use of AC influences almost every aspect of today's technology. From the computers in this classroom to the cellular telephone in this car. From arcade games and microwave ovens to satellite communications.
There is hardly an aspect of your everyday life that isn't influenced in some way by AC. The widespread utilization of AC can be grouped into 3 general categories of usage: for electrical power, for electronics, and for communications. Let's take a closer look at each one, beginning with electrical power. This is the type of AC usage you're probably most familiar with. Many devices, motors, appliances, and machines access alternating current directly for power through being plugged into a wall outlet.
The second general category of AC usage is for electronics, which uses alternating current in a different way. Here, the incoming AC signal is not used directly, but is altered. Although AC power enters the unit through the power cord, as in the case of this VCR, it is immediately modified by certain components so as to be useful to the microcircuitry.
A third general category of usage is communications. AC is capable of producing radio waves, which can carry information through space. This kind of AC makes satellite communications and space exploration possible, as well as operating the remote control devices used in model cars. Cellular telephones communicate with each other using this type of AC too.
Although thinking about AC usage in terms of these 3 general categories can be useful, it's important to realize there's a good deal of overlap among them.
For example, a television alone utilizes AC in all 3 different ways. AC powers it. The internal circuitry of the power supply converts AC for use by the microelectronic circuitry. And an AC signal carries the programming, which is received through the television's antenna.
As you can see from such widespread usage, understanding AC fundamentals will open the door for you in any field of electricity, electronics, and communications. Let's begin our exploration of AC fundamentals by looking at magnets. Without magnetism and its relationship to electricity, all of the electrical devices and applications just mentioned would not be possible.
Knowing the properties of magnetism will help you in your understanding of alternating current. In this video, the physical aspects of magnetic fields will be presented. The relationship between magnetism and electricity will be introduced. You'll see what an electromagnet is, and you'll be introduced to some common electrical devices that depend on magnetism for their operation.
The first known magnets were found in a natural state. These were stones composed of iron ore called magnetite, which had the unusual ability to attract small pieces of some metals. Today, there are man-made magnets. These are more powerful and more conveniently shaped.
No doubt you've seen how a magnet can influence certain metal objects at a distance. This is because it has an invisible, 3-dimensional force field surrounding it, known as a magnetic field.
Iron metal filings can be used to show the magnetic field. Here, a bar magnet is placed under a piece of paper. Then, iron filings are lightly sprinkled onto the paper over the magnet. Because the iron filings are a magnetic material, they arrange themselves along the paths of the magnetic lines of force. Notice the distinctive pattern of the magnetic field. Here's a 2-dimensional graphic representation of a magnetic field using dashed lines. But remember that a magnetic field in reality is 3-dimensional.
Magnetic fields have some very specific characteristics which play important roles in the production and use of alternating current. Let's see what they are.
Magnets have polarity. Polarity means that the characteristic of the force at one end of a magnet is different from, or opposite to, that of the other end. When this bar magnet is brought close to these iron filings, it's clear to see that most are attracted to the ends of the magnet. Most of the magnetic force is concentrated at the ends or poles of the magnet. There's a north-seeking pole, designated N, and a south-seeking pole, labeled S. These poles correspond to the Earth's magnetic poles. The Earth is like a very large magnet, with a north pole and a south pole.
There are different theories about what creates magnetic polarity. One widely accepted theory is based on the direction in which the electrons within a material are spinning on their axis as they orbit the nucleus of an atom. The theory states that the action of the spinning electrons produces a magnetic field. In non-magnetic materials, there are roughly equal numbers of electrons spinning in opposite directions, and consequently, they neutralize each other's magnetic effect. In magnetic materials, there are more electrons spinning in one direction than in the other. This excess of spinning electrons creates the magnetic force. When a large number of these magnetized atoms group together with their magnetic fields aligned, they form domains, represented here by boxes in a grid. Each domain has its own north and south poles, which in an unmagnetized substance are randomly arranged. Only when the magnetic poles of the separate domains become aligned does the material as a whole become magnetized with a north and a south pole.
Perhaps you remember being warned that mishandling a magnet would cause it to lose its magnetic power.
For example, if a magnet is repeatedly dropped, or if heat is applied to the magnet, the domains will be jarred into a random arrangement, demagnetizing the metal. In demagnetized materials which no longer have any overall polarity, the domains are scattered at random.
Let's look at another important characteristic of magnetic fields.
The lines of force flow in a specific direction, forming complete loops. The lines of force are assumed to flow in one direction, from the north to the south pole outside the magnet, and then continue right on through the magnet from the south to the north pole.
Another characteristic is that magnetic lines of force always tend to form the smallest loop possible. Like stretched rubber bands, the lines of force always try to contract toward the surface of the magnet.
A final characteristic is that magnetic lines of force never intersect. The lines of force will always run parallel.
These are important characteristics of magnetic fields because they affect how alternating current is generated and utilized. Be sure to keep them in mind. Now let's see how magnetic fields interact first with each other and then with different materials.
You may have tried experimenting with two magnets and noticed how they would either attract or repel each other. This happens because their magnetic fields are interacting. This interaction is determined by the second characteristic of magnetic fields that you were shown, the specific direction of the lines of force. Remember that the lines of magnetic force are assumed to exit the North Pole and re-enter at the South Pole outside of the magnet, and pass from South Pole to North Pole within the magnet. Keeping this in mind, when like poles are placed near each other, the direction of the lines of force are in opposition, pushing away or repelling one another. Conversely, when unlike poles are brought in proximity, the lines of magnetic force extending out of the North Pole of one magnet coincide perfectly with those that are passing into the South Pole of the other magnet, drawing them together. When the magnets touch, the two fields join together and form one magnetic field. The lines do not intersect, but run parallel to each other.
To sum up, unlike poles attract and like poles repel. These two laws of polarity give magnets their usefulness. Now, let's see why magnets attract certain materials and not others. You've already seen how iron, in the form of filings, is attracted to a magnet. But why? Let's work with something larger in order to find out.
Watch what happens when this nail is positioned near the north pole of the bar magnet under the paper and iron filings are sprinkled on top. Notice that the filings form a different pattern here, indicating that the shape of the magnetic field has been altered. This is because, as compared with air, the nail provides an easier path through which the magnetic lines of force can pass. The ability of a material to permit a magnetic field to be established within it is called permeability.
Reluctance, on the other hand, is a material's tendency to oppose the passage of a magnetic field. Notice that, for example, when the magnet is held at this distance, it has no effect on the filings. This is because air has a much greater reluctance rating than iron or steel. But watch what happens when a metal paperclip is added. Because the metal has a greater permeability than air, the magnetic lines of force become concentrated within the paperclip, thereby attracting the filings. The greater the permeability of a substance, the stronger the resulting magnetic field within it will be. The paperclip has become magnetized through a process known as magnetic induction. Because of this, the paperclip is capable of magnetically affecting the iron filings. If it were to remain attached to the magnet for a long enough period of time, the paperclip would eventually become magnetized itself. But without the magnet, there is no magnetic attraction because the magnetic field is not passing through the paperclip.
Materials that affect a magnetic field are known as magnetic or ferromagnetic materials. These are strongly attracted by a magnet and include nickel, iron, cobalt, and alloys made with these metals. When these materials are subjected to a magnetic field for extended periods of time, they become permanent magnets. A permanent magnet retains its magnetism indefinitely unless mishandled.
Let's see how a different material affects the magnetic field.
Notice that this piece of wood has no effect on the iron filings. Materials that can't influence the shape of a magnetic field, such as copper, brass, aluminum, wood, glass, and most plastics, are referred to as non-magnetic materials.
Now, let's see how the strength of a magnetic field can be determined.
Groups of force lines within a magnetic field are called magnetic flux. The more lines of force, the greater the magnetic flux, and the stronger the magnet. A single line of magnetic flux is called a Maxwell. Magnetic flux is measured in Webers, abbreviated WB. 1 Weber is equal to 100 million lines of force. The lowercase Greek letter phi is used to represent the number of lines of magnetic force in Webers. But with Webers being such a large unit, a more common unit is the microweber, abbreviated μWb. A microweber consists of 100 lines of magnetic flux.
You can determine the strength of a magnetic field by finding the number of lines of force in a given area. The greater the number of lines, the greater the power of the magnet.
The determination of a magnetic field strength is known as flux density and is identified with the capital letter B. This is the amount of flux per unit area. 1 Maxwell passing through 1 square centimeter is called a Gauss. As an example, a strong permanent magnet might have a field strength of about 10,000 Gauss. A larger unit of flux density is the Tesla, identified by the capital letter T. The Tesla is equal to 1 Weber per square meter, that is, 10 to the 8th magnetic lines of force passing through an area 1 meter by 1 meter. Use this formula to calculate flux density of a given magnet. B sub T, the flux density in Tesla, equals phi divided by A. Phi is the number of lines of force in Webers, and A is the cross-sectional area of the magnetic path in square meters.
Let's find the flux density for an iron core whose cross-sectional dimensions are 20 millimeters by 30 millimeters and whose total flux is 3 Webers. First, millimeters must be converted to meters. 20 millimeters equals 0.02 meters, while 30 millimeters equals 0.03 meters. To find the area, multiply the height times the width. This yields 0.0006 square meters. The final division yields 5,000 T as the flux density.
The main idea in performing the calculations to determine magnetic strength is to recognize that there are a number of interdependent variables that can affect the relative strength of the magnetic field. Perhaps by now you're wondering what magnetism has to do with electricity. In fact, they're linked very closely. Let's see how.
Electricity produces magnetism. Any conductor that carries an electric current will act like a magnet. Let's use iron filings again. Watch what happens when a wire, which is connected to a DC source, is brought in proximity to the filings. Notice how they're attracted to the current-carrying wire as if it were a magnet. This is because when current flows in a wire, a magnetic field is produced around it. When the wire is disconnected from the DC source, the iron filings are released. The wire was temporarily magnetized by the electricity. The process of creating magnetism with electricity is known as electromagnetism. Look at the word. Notice that it's really two words combined, electro and magnetism.
The current-carrying conductor that attracted the iron filings is a very simple electromagnet. Let's examine the electromagnetic field more closely.
Here, a heavy copper wire has been inserted through a sheet of cardboard and connected to a DC source. Let's use a compass to determine the direction of the magnetic field caused by the flow of electricity. A compass is a device for determining direction by means of a magnetic needle that turns freely on a pivot. The colored part of the needle will always seek the Earth's magnetic north. Place the compass in proximity to the wire inserted through the cardboard and note the direction that the needle is pointing. Continue moving the compass to various positions around the wire, noting the direction of the compass needle at each point. The record of compass readings will indicate the direction of the magnetic field. Notice that in this graphic, the current is flowing downward through the wire from negative to positive. If the polarities are reversed, the direction of the magnetic field caused by the current flow will be reversed.
The direction of this circular magnetic field around the conductor is important for the operation of generators and motors. Here's a simple way to determine its direction. This length of insulated wire will be used to demonstrate. Curl the fingers of your left hand as if you're grasping the insulated conductor. Make sure that your thumb is pointing in the direction of the electron current flow. In this position, your fingers will automatically be pointing in the direction of the magnetic lines of force around the conductor. This is called the left-hand rule for conductors. Do not attempt to do this experiment without the supervision of your instructor. Electrical current can be potentially dangerous. The magnetic field produced by a small amount of current passing through a straight wire is weak and of little value.
The magnetic field produced by a current-carrying conductor can be reinforced or made even stronger if the wire is first wound into a coil. You can see how the magnetic field is strengthened in a coil by looking at this graphic representation of parallel conductors. Notice that lines of force pass around the conductors in the same direction. Because of this, the fields of each conductor add together to form one large field that envelops all of the conductors. Just as with a single conductor, when the polarities are reversed, the direction of the magnetic field is reversed as well. When a number of loops are wound in the same direction to form a coil, the magnetic fields of each loop interact to make the flux lines through the center of the coil more dense. The magnetic field through the coil becomes stronger. This produces magnetic poles with north on the end where the flux lines come out and south on the end where they go in.
The strength of the resulting magnetic field depends upon two things: the number of turns of wire, designated N, and the amount of current I.
For example, the strength of an electromagnet can be doubled by increasing the turns of wire from 40 to 80, or by doubling the current from 2 amps to 4.
In order to compare the magnetic strength of different coils, the magnetizing force must be determined.
This force, caused by the current flowing through the coil, is called the magnetomotive force, abbreviated lowercase m, lowercase f. The unit of measure for magnetomotive force is ampere turns, abbreviated with a capital AT. The magnetomotive force can be found using this formula: mmF equals I, the current in amperes, times N, the number of turns. For example, a coil with a current of 5 amperes and with 20 turns has a magnetomotive force of 100 ampere turns. Another coil with a current of 2 amperes and with 50 turns also has a magnetomotive force of 100 ampere turns. The magnitude of the magnetomotive force determines the number of flux lines there will be in the magnetic field. As the magnetomotive force is increased, the number of flux lines also increases. The strength of a magnetic field around a coil depends not just upon the amount of current or upon the number of turns, but upon both.
The magnetic field produced by a coiled current-carrying wire can be further increased by first inserting a piece of ferromagnetic core through the center of the coil. Remember, ferromagnetic materials have a higher permeability than air, which means that these materials permit the passage of many more magnetic lines of force than the surrounding air will. The material inserted into the coil is called the core. It concentrates the coil's magnetic field. Soft iron is used as a core in an electromagnet such as this one because it will retain only a small amount of its magnetism when the electric circuit is opened. This is called a temporary magnet.
You cannot control the output of electric generators and motors if you can't control the magnetism.
Temporary magnets are important. The electromagnet carried by this crane must be magnetized to pick up the metal and then demagnetized to let it go.
There are some devices that depend on principles of electromagnetism.
A solenoid is a device that enables an electric current to control a mechanical operation. A solenoid can be thought of as an electromagnet that has a movable iron core. Another important device is a relay. A relay is an electromagnetic switch. Unlike a mechanical switch, a relay can be located anywhere and operated remotely. As current flows through the relay coil, the magnetic field of the coil pulls down the armature, causing the contacts to close.
Let's look at one more device that depends on the principles of electromagnetism: permanent magnet speakers, which are commonly used in radios, stereos, and TVs.
A permanent magnet speaker is made from a paper cone and a permanent magnet. As you can see on this cutaway speaker, the flexible paper cone is attached to a cylinder with a coil of wire around it. One of the poles of the permanent magnet is positioned within the cylindrical coil. When current flows through the coil, it creates a magnetic field that interacts with the magnetic field of the permanent magnet, causing the cone to move in and out.
The speaker you are listening to right now uses the principles of magnetism and electromagnetism. Let's stop here and review what you've been shown.
In this video, you've been introduced to 3 main uses of AC: for electrical power, for electronics, and for communications.
The basic characteristics of magnetic fields were discussed.
You've seen how magnetism and electricity are related. The principles behind electromagnets were presented.
Finally, you were introduced to some devices that depend on electromagnetic principles for their operation.
In the next video, you'll see how generators produce electricity using magnetism and how electric motors use magnetism to develop their rotational power.